Hello, guys. Hello, everyone. Am I audible? Am I audible, guys? Just tell me in the chat. Okay, thank you. So, hi, everyone. Welcome to today's PCD of CF round 1018, which was Div 1 plus Div 2. We will discuss the first four problems. My name is Pradyumn Kejriwal, and let's begin. So, before we start, I will tell you about our all new CP31 sheet. Okay, so if you don't know already, this sheet contains 31 handpicked problems in each rating from 800 up to 1900, and they are picked in such a way that each problem teaches a unique idea. All right. Further, you can connect your CF account to this sheet, so you can easily see and track that which problems have been solved by you on Codeforces. Also, each week, 7 to 8 solutions will be uploaded on YouTube, so you won't have to search for them at some other places. Also, there's a leaderboard where you compete with your friends and peers about who solves more problems. All right. So the link to the sheet is right below. So let's start with the first problem of today. Okay, it's called Wonderful Sticks. You are the proud owner of n sticks. Each stick has an integer length from 1 to n. The length of the strings are distinct. You want to arrange the sticks in a row. There is a string s of length n minus 1 that describes the requirements of the arrangement. Specifically, for each I from 1 to n minus 1, if s of I is less than symbol, so the string only contains less than and the greater than symbols. So if si is less than symbol, then the length of string the length of the stick at position I plus 1 must be smaller than all the sticks before it. And if s of I is greater, then the length of the stick at the position I plus 1 must be larger than all the sticks before it. Find any valid arrangement of sticks. We can show that an answer always exists. Okay. So, yeah, the problem says that basically you want to arrange the sticks, like you have the sticks from of length 1, 2, 3 up to n, and you want to arrange them in the order, like not in some order, but in with some requirements. Okay. So there's a string of length n minus 1 which has only this character and this character, right? And what you have to do is, for all, like if s of I is equal to this character, okay, then your a of I plus 1 has to be less than all of a1 to up to ai. Okay, so it has to be less than all of them. And if s of I is greater, so if the string of I has this greater than symbol at the ith place, then your a of I plus 1 has to be greater than all of a1 up to ai, right? So you have to print any valid sequence which has only the elements from 1 to n. Okay, so guys, let's look at a sample. Let's say that we have this sample: less less greater less. Okay, so this is a sample: less less greater and less. So actually the entire idea here is that we can simply output any random arrangement, like any random array, and then try to compress it to the range 1 to n. Okay, so what I'll just try to do is arbitrarily make an array which satisfies these comparison constraints, like which satisfies these constraints that a of I plus 1 has to be less than all of a1 to ai, or a of I plus 1 has to be greater than all of a1 to ai. But what I will do is, like, I will ignore this condition that they have to be between 1 to n. I will handle this later. Okay. So for now, what I'll do is, let's say I have to place 5 numbers, right? So let's say I place 0 right here. Now this first element, this first string, the string's first character says that this letter right here has to be less than all of the letters that have appeared till now. or this number right here, I mean, has to be less than all of the numbers that appear till now. So till now only 0 has appeared, right? Till now only 0 has appeared. So I can place -1 here. So this is done. Now we come here. This also wants that uh, this number right here has to be less than all of the numbers that have appeared until now. So until now, -1 and 0 have appeared. So what we can do is write -2 here. So we'll get -2 and 0 that have appeared till now. Okay. Then we have that at this point, the number which is here has to be greater than all of these three numbers. So we have the numbers from -2 to 0. So we can place 1 right here. So we'll have all the numbers from -2 to 1. And then finally, here we have that this number has to be less than all of these numbers. So we can place -3 here. Right. So this is my array. But it is not my answer, because in my answer, I want that all of the numbers should be in the range 1 to n. Right. So what I can just do is I can, like, there are many ways to do this. What I can do is maybe I can make a vector of pair and sort it. Like, then basically -3 will be at the position 1, right? If I sort this array, then -3 will be at the position number 1, -2 will be at the position number 0, or sorry, 2, -1 will be at position 1, 0 will be at position, what I'm sorry, 1 2 3, then 0 will be at position 4, and 1 will be at position number 5. So what we can just do is at -3 I can write, instead of -3 I'll write the position of -3, so that will become 1. Then at -2 I'll write the position of -2, which is 2, and so on. So I will get basically 1 2 3, sorry, not 3, 3 4 and 5. So my answer is this: 4 3 2 5 1. Right. So this is one method, but this is tougher to implement than what I am going to tell you right now. So what I did was, like, let's say you have this array, right? You have this array which you have made, and also you have this range. Sorry, this is not your array. Yeah. So the array is this. The array is this that you have made, right? And what you know is that in this array, all of the elements are contiguous, right? Like, that's how you build this array. Like, you know that all of the elements from -3 to 1, all of the elements from -3 to 1 appear in this array, and that's why what you can just do is add 4 to all of the elements. Like, just add 4, so that the minimum element, which is -3, becomes 1. So what we will get is 4 3 2 5 and 1, right? And adding 4 does not change the order of the elements, right? And that's why, if this satisfies the constraints, these constraints, then if I add 4, then also it satisfies these constraints, right? That's what I can say. So that's what I'm doing. I'm just keeping track of this range, that what I'm currently at. So I'm just keeping an L and an R. Okay. So let's run this on another test case. Like, let's say we have this test case. Greater, less, greater, 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 and less, right? So initially I will place 0 here. Then we want less than, so -1. Then we want greater than, so we'll have 1. Then we want greater than, so we'll have 2. Then we'll have 3, and then we'll have -2. So we will add 3 to this entire array. Like, the minimum number is -2, right? So we'll add 3 to the entire array. So what will it become? 3 2 4 5 6, and actually I made a mistake in copying, I think. Greater, less, 3 times greater, and less. Okay, sorry, I missed this greater. My bad. Okay, so we place a 0 here, and the first symbol is greater. So we'll write 1 here. Then it is less than, so we'll write -1. Then it is greater, so we'll write 2. Then it is greater, so we'll write 3. Then we'll write 4. and then we'll write minus 2, right? And then we'll add just 3 to get in the range. So 3, 4, 2, 5, 6, 7, and 1. So this is your answer. Okay. So yeah, this is my solution. And how do you implement this? You can simply keep an active range of L comma R. So you can initialize L to 0 and R to 0, right? And initially, what you will do is in your answer array, you will keep a 0 here, right? Then you will iterate over the string S. Okay. So let's say you had some string less, greater, greater, less, greater, greater. So when you are at less, you want that all of the numbers from L to R, your current this number has to be less than those all of those numbers. So just set it at L minus 1. Like just put L minus 1 here and then decrement the L. Like let's say you put minus 1 here and you change this to minus 1. Now let's say you want greater. So you will place R plus 1 here, which is 1. And since you have 0, 1 to minus 1, so you will update R to 1. So minus 1 to 1, and so on you will do. So yeah, that is the algorithm here. So does anyone have a doubt in this? Like in the idea of the algorithm or the implementation? Like I'll show the code, of course, but in the logic part, does anyone have a doubt? Uh, HFZSR. Like I don't know how to pronounce that, but your solution is also right, of course. But I think my implementation is a bit easier. I'll show the implementation. Okay, so yeah, this is the code. Int n, c in n, string s, c in s, and this is my answer vector. Okay, vector of LLVN. Now I just set v of 0 to 0, and our initial range is L comma R, which is 0 and 0. Now I'll do for int I equal to 0, I less than n minus 1, I plus plus. So I'm iterating over the string s. Now if s of I is the less than symbol, then I will do v of I plus 1 is equal to minus minus L. So what does this do? This does that it decrements the L and it returns the new value of the L. So minus minus L decrements the L and it just stores the new value of L in v of I plus 1. So just decrementing and setting, I am doing it in just one line, right? And if s of I is greater operator, then I will do v of I plus 1 equals to plus plus R. So that also does the same thing, that it increments the R and it sets the new value of R to v of I plus 1. And then I'll just print v of I minus L plus 1. Since we want that, see, the minimum value is L, right? In the v vector, minimum value is L. Like somewhere there will be L, right? So we want this to be 1. So what we'll do is we'll add minus L plus 1. We'll add minus L plus 1 to the entire array. So this value becomes 1 and all of the other elements stay in the range. Okay. So yeah, this is the solution. So if someone has any doubt, then please let me know. Nice. Exactly. It is pretty elegant. What was your rank? My rank, I think around 720-ish. Okay, problem B. Let's go. Problem B is called Wonderful Gloves. You are the proud owner of many colorful gloves, and you keep them in a drawer. Each glove is in one of n colors, numbered from 1 to n. Specifically, for each eye, you have Li left gloves and Ri right gloves with color I. It is late night, so you cannot see any of your gloves. In other words, you will only know the color and the type of a glove after you take it out of the drawer. Okay. A matching pair of gloves with color I consists exactly of one left glove and one right glove with color I. Find the minimum number of gloves you need to take out the drawer to guarantee that you will have at least k matching pairs of gloves with different colors. Formally find the smallest positive integer such that for any set of X gloves, yeah, formally whatever. Yeah, so what we have to do is that, um, okay, so basically we have n colors of gloves. Okay, so we have gloves of n different colors. All right, and basically for the ith color, we have Li gloves of the left hand and Ri gloves of the right hand, and we have to simply print the minimum number of gloves. Minimum number of gloves we need to pull out. We need to pull out to ensure that we can get a matching pair. And matching pair is defined as the same color, like a same color, and one is left and one is right. Okay. So before solving this, I will tell you a simple problem. Okay. A simpler problem is what? Let's say you have socks of k colors. Okay. So as you may know, socks don't come in right or left. Like maybe they come, but I don't know. But socks, let's assume that socks are identical. Left and right are identical. So left and right are the same for socks. Okay. So let's say you have socks of k colors. So you have, let's say, in a drawer, you have socks of k colors. Let's say A1 socks of color 1, A2 socks of color 2, and up to AK socks of the kth color. Right. So you want to find out that at least how many colors you want to pull out so that you can get a matching pair. Okay. So actually this is one even simpler problem. Actually in this problem you have to guarantee that at least k matching pairs are there. Okay, at least k are there. But in this problem I am first assuming that there are no left and right, all of them are same, like the only difference is of color. Okay, so I am dealing with socks and not with gloves, so left and right are same, and the difference is color. Like we have k colors and we have A1 A2 AK, like we have A1 socks of the first type in our drawer. This is a drawer. Okay, and you cannot see in the drawer. So you have A1 socks of first type, A2 of second type, and AK of the kth type of the kth color. So just tell me that how many socks, minimum socks to pull out to ensure you get one matching pair. Like at least one. Okay, at least one matching pair you want. Okay, so this is one problem that you can solve. This is an easy problem. So we have A1, A2, A3 up to AK, right? So we want that at least one matching pair appears. So guys, what will be the answer to this? Like, can anyone tell me the answer? That you have k types of socks, and of the first type you have A1 socks, second type you have A2 socks, and so on. You have AK socks, and what is the minimum number of socks that you can pull out? You have to pull out to ensure that you have at least one matching pair. K plus one, correct. So the correct answer is k plus one. Why? I mean, it is pretty obvious, right? Like You can call it like, maybe you can use the pigeonhole principle. Like, you can call it that, but it is pretty obvious that there are only k types of colors, right? There are only k different colors. So if you pull out k plus 1 colors, k plus 1 socks, then of course at least one of them will have what? Will have the same color. Like if you have two pairs of, let's say you have 5 colors and you pull out 6 socks, then of course out of the six, all of them cannot have different color. At least one of them will have the same color. So that's why your answer is 5. Sorry. Max plus 1. Actually, yeah, this was a different problem. My bad. So just forget all of this and don't write anything mean in the comments, please. Uh, okay, so this is not the correct answer. Actually, A1, A2, A3, up to AN. You have these number of socks. Just a minute. Okay, no, it was correct, right? Why is everyone saying max plus 1? I got manipulated also. Why is everyone saying max plus 1? Like, I think the answer is just k plus 1, right? If you pull out k plus 1 socks, then of course, uh, at least one of them will have k, right? And like if you pull out only k socks, let's say you pull out only k socks, then it might happen that the first sock is of a different color. Let's say of color 1, then second is of second color, then third one is of third color, and up to kth color. Like it might happen that you pull out k different colors, and with k plus 1 socks, of course you will pull out at least one pair. Yes, it is k is the number of types. K is the number of types. So if you want, see, how do I explain? Let's say you have, I'll draw a bag, okay? I'll draw a bag and I'll use 4 different colors to explain. So let's say you have this one sock, and let's say 2 socks of color 1. Then color 2, you have 3 socks. Then the third color, you have, let's say, 3 socks. And the final fourth color, you have only one sock. So if you want that you have at least one pair, so if you pull out at any 5 socks, okay, so let's say you pull out these 5, then you will have a pair of white and red and red. So if there are 4 types of colors, like let's say I tell you that pull out 5 socks and none of them should have same color, no pair should have same color. So can you do it, Abhinav Enala? Like Abhinav Enala, can you do this? Take red equals to 4, okay. Abhinav, I took red equals to 4. So can you pull out 5 socks such that none of them have the same color? Like what color of socks will you pull out? Like you have to pull out, just tell me 5 colors which you pull out. No, exactly. So it doesn't matter like what numbers you have. If you just pull out k plus 1 socks, if you pull out k plus 1 socks, then okay, Abhinav says, what if I take all red socks in the worst case? Yes, so you want the same color, right? You want that at least two of same color should happen. Like I think max plus 1 is the answer for different color. Like if you want that at least one pair should have different color, then it is max plus 1. But if you want that at least one pair has same color, then it is k plus 1. Abhinav, do you get this now? Like, what was the problem? That the problem was that you have to get at least one matching pair. So if you pull out all four reds, then these two are same, or maybe these two are same. So you have two reds, right, to wear. Got it? Cool. So yeah, basically this was one problem. And actually, how did we solve it? Let's think about that. Actually, how did we solve? Basically, um, what we did was took the worst case, right? We took the worst case, that how many socks can we pull out, such that, okay, what we asked ourselves was how many socks can we pull out, such that we don't get any pair. We don't get any pair. So how many maximum number of socks? So this is, we have to maximize. How many max socks can we pull out such that we don't get any pair? So in the worst case, of course, we can pull out k different number of socks. Like we can pull out this one sock, then this one sock, this one sock, and this one sock. So we can, in the worst case, we can pull out k socks and we still won't have any pair. So that means that if we pull out k plus 1 socks, like basically whatever answer we got for the worst case, so whatever answer we got for the first case, we can just do answer plus 1. So answer plus 1 is our answer for what is the minimum number of socks that you need to ensure that at least one pair is there. Correct. So this is the thing, right? That's what the observation I want to tell you, that um, if you have the answer for the worst case that we don't get any pair, then answer plus 1 is just the minimum number of socks, such that you get at least one pair, right? So that is my point. So let's try to do this in this problem. Okay, so this problem was that you have to have at least k matching pairs with different colors. Like, so essentially what it is saying, okay, so let us look at the test case. Let us look at this test case. Okay, so you have, on the first color, of the first color, you have one L and one R. Of the second color also, you have one L and one R. And third color also, you have one L and one R. And your K is 3 in this case. K is equal to 3 in this case. So they are asking you that at least how many gloves you have to pull out, so that you will have at least K matching gloves of different colors. Okay, so let's say you had two LRs. Okay, so they are asking you that um how many how many gloves should you pull out to ensure that there are at least k different pairs of gloves, like of different colors, right? So let's solve for this test case. Okay, so guys, tell me, if I pull out like six socks, if I pull out six socks, can you guys construct a case where I do not get at least three distinct pairs? Like, can you guys construct a thing where I don't get three distinct pairs? So I want that three different pairs of gloves I get, right? So if I pull out any six gloves from the drawer, is it possible that I don't end up with? Yes, Anuj can. So what? How can we do this? Actually, we can do this like this. So let's say we pull out these socks, like these six socks. We pull out. So in that case, we'll only get two pairs, right? We only get this pair and this pair, right? So that is the problem here, that we cannot ensure that we are always getting at least 3 pairs. Okay. But what if I pull out 7 socks? What if I pull out 7 socks? So then can you guys ensure that I get at least 3 distinct pairs? Like, can anyone ensure? Can you? Okay, so my question is that if I pull out 7 socks, so can you guys make a test case, or can you guys make any case so that I don't get at least 3 pairs of socks? Okay, so Harsh is saying no, Rajat saying no, Vinay saying no, Devang saying no. Anuj, can you do that? So if I pull out 7 socks, can you get 3 distinct pairs, or can you not get 3 distinct pairs? I mean, can you make a case where I'm not getting 3 distinct pairs? 2 pairs of red, 1 pair of green, and 1 yellow. Yes, exactly, Guru Prasad. So we cannot get 3 distinct pairs. Like, if we just put out 7 socks, it is possible that we are not getting 3 distinct pairs, because here I'm getting only two, right? I'm only getting a red and a green, right? So that's why even with 7 socks, we cannot ensure that we are always getting um, 3 distinct pairs. But of course, if I pull out eight, like if I pull out 8 distinct pairs, or if I pull out 8 socks or 8 gloves, then I can be sure that I will have 3 distinct pairs. So therefore, the answer to this case also will be 8. This case. Okay, so I think the problem is clear now, that what we have to do, right? So the notion that I told you here, that if we know that what are the maximum number of socks or what are the maximum number of gloves, like for this test case, let's try to solve this problem, that what are the maximum number of gloves that I can pull out, such that I don't get k distinct pairs. Like, let's solve for this, that what is the maximum uh, number of gloves, such that I don't get k distinct pairs, right? So of course, like, the since we know that the answer to this test case was 8, right? So that means that the answer to this question would be 7, because we know that 7 plus 1 is 8. Like, if the answer to this is answer, then our actual answer is answer plus 1. So yeah, anyways, so yeah, let's solve this, that what is the maximum number of gloves such that I don't get k distinct pairs. So what do I mean by that? So let's say that we can get at most k minus 1 distinct pairs, right? Like, let's say k is 3 here, right? K is 3 here. So we don't want k distinct pairs. So if we have 2 distinct pairs, then it is fine, right? So we can have 2 distinct pairs. So now, out of these three, which 2 distinct pairs should I have? So let's say I get a red distinct pair and I get a green distinct pair. Okay, and I don't get a yellow pair. So if I am getting a red pair and I want that the maximum number of gloves I pull out, like what is the maximum number of gloves that I can pull out, then of course I'll just pull out all the red ones. I'll pull out all of the red ones, right? Because anyways, I am getting a if I am getting a red pair, then I want to maximize the number of gloves, right? So I'll just pull out all of the red pairs, all of the red gloves. And if I want that this green is there, so I'll pull out um, all of the green ones also. But this last pair I don't want. Like, I don't want that yellow has a pair, so I'll just pull out one. Like I'll only pull out this left one. But let's say there were multiple yellow ones. Okay, so let's say there was LR, LR, and there was one R also. Okay, so what would I do? What would I do? I don't want this yellow pair, right? I don't want this yellow pair. So I'll just select those four R's. So I won't get any pair of yellow, but I will get a pair of these two as well. Like I will get these two pairs, these two distinct color pairs, but I won't get any pair of yellow. So I can basically select 10 gloves, right? But actually, we can do even better. We can do even better. How? We can simply uh, like we want to make two pairs, right? We want to make two color pairs, so we can make a yellow one, like we can make yellow ones and the red ones, right? And we don't make green ones. So if we want to not make green ones, then I'll just take one of them. So in this case, how many did I choose? 1 2 3 4 5 6 7 8 9 10 11 12, right? So at max we can choose 12. So like now the problem is that how do we figure out that which to choose? Like if we want k minus 1 distinct pairs, right? We want k minus 1 distinct pairs. So which colors should we choose? We have to choose k minus 1 colors, and we'll just take all of them, like all the gloves of that those colors. And for the other colors, I'll take only one side, right? So let's say I have some other test case. Let's say I have this test case 2 3, like the color 1 has left gloves of two types, like two left gloves and three right gloves. Then I have a color 2 of three left gloves and one right glove. Then I have a color 3 of four left gloves and five right gloves. And I have color 4 also of 10 left gloves and um let's say one right glove. Okay, and I want, and like my k value is 3. So let's try to solve this. Okay, so I want that I get at least three distinct pairs. So what do I solve? That what is the maximum number of gloves, so that I only get, like I don't get three pairs. Like I don't get three pairs. So let's say I get two pairs. Like in the worst case, I can get two pairs. So which two pairs should I choose? So what I claim is, like let's try to take that these two pairs. Let's choose like the color number one and color number three. The color number 1 and 3, I will say that okay, I got their pairs. So I will take all of these gloves. So 5 and this 9. I'll take all of these gloves. 5 plus 9. But okay, for the other colors, this 2 and 4, I don't want that they form a pair. So I'll take only the left or only the right. Either only left or only right. So what I'll do is I'll take only the left in this one and only the left in this one, because they are greater. The left ones are more. So I'll take these 3 and I'll take this 10, right? So I'll get my answer as 14 plus 3, 17 plus 10, 27. And my actual answer is 28. Like this is the maximum number of uh, gloves that I can pull out, so that I will not have k distinct pairs. So if I pull out 28, then I'll definitely have k distinct pairs. Okay, but so now how do we choose? The main question is that how do we choose? So to do that, actually, it is very simple actually. So I'll just take a general case. Okay, let's say you have L1 R1, L2 R2, L3 R3, L4 R4, and L5 R5. So let's say the value of k is k. Okay, value of k is k. So uh, let's say you want k minus 1 pairs, right? You want k minus 1 pairs. So you will choose some k minus 1 numbers, like you will choose some k minus 1 colors to make a pair, and the rest of the ones, the rest of them won't be in a pair. So how many are left? Like you have n colors, right? You have n colors, and out of them k minus 1 are in a pair. So n minus k plus 1 are not in a pair. N minus k plus 1 are not in a pair. So what will you do with them? Like let's say n minus k plus 1 ki value is 2. Let's say that. Like let's assume that the value is 2. So you want to choose uh, two colors that are not in a pair. Okay. So let's say you chose these two. Like you chose the color 2 and the color 4. So what you will do is you will just take the maximum. Like see out for the other colors, you will take all of these gloves, and for these two colors you will take the maximum, right? Whatever is the maximum of L2 and R2, and whatever the maximum of L4 and R4. So what you haven't taken, like what you haven't taken is this R2 and L4, right? And basically you want to maximize what you have taken. You want to maximize what you have taken. So essentially you have to minimize what you have not taken. So you have to minimize this R2 and L4, right? So like what you will do is, if you have L1 R1, L2 R2 up to Ln Rn, and let's say, see, you want n minus k plus 1 non pairs, right? So let's say this is some value u. Okay, you want u non pairs, and for all the non pairs you will simply take the maximum, right? So let's say the indices like I1, I2, I3 up to IU, like these indices you don't make a pair. So what you will do is, for these indices you will take the maximum of ri1 comma li1. So if ri1 is bigger, then you will take the right one, and if li1 is bigger, you will take the left one. So this you will take from all of these. So what does that mean? You will leave the minimum of ri1 and li1. So you will leave these number. So and you want to minimize this, like you want to choose these indices which minimizes the sum, right? So you can just greedily take the minimum of all of them. Like let's say you have some test case 100, 1, 10, 10, and 2, 4, and 3, 0, or 3, 1, let's say, and you want to have two pairs, okay, and two non pairs. So you will choose these two because their minimum is 1. Like this minimum is 10 and this minimum is 2, and these minimums are 1. So obviously you will choose these two minimums to leave out. So you will leave out these, and your final answer would be the sum of these numbers. So what the final algorithm is, that for every color, sorry, 1 minute. For every color, what you will do is you will take the minimum. Like let's make a new array which is the minimum of these. So the minimum of 101 is 1, minimum of this 2 is 10, minimum of these 2 is 2, and this is 1. So if you want that, let's say you want to make two non pairs, so you will take these two. Like basically you will sort this vector and take the first two, and what is that? That value is just what you are not picking. Like you are not picking these two ones, you are only picking these 6 remaining elements. So your final answer would be just the total number of gloves, like total number of gloves minus what you are not picking, right? And this is the maximum number of gloves that you can pick to ensure that you don't get k pairs. So if you do plus one, then that is the minimum number of gloves you can pick to ensure that you get at least one k. You get at least k pairs. I mean, so this is your final answer. So do you guys get this? Or I think I have explained it quite a lot. Like you can just make the minimum array of this 1 10 to 1 minimum array and sort this and get the first n minus k plus 1 elements, because you want these many non pairs. You want these many non pairs, so just pick them. And so basically, the first these many elements you are not picking. So the final answer is total minus what you are not picking plus 1. Okay. So yeah, I think it should be clear. I'll show the code. So the code is this. It is pretty small. Int nk scene nk. I'll take the input of arrays L and R. So this is my macro actually, which just makes the arrays and takes the input of them. And I have a new vector of v for int I equal to 0, I less than I plus plus. And I'll make the new array of minimum of li comma ri. And then I'll sort this new array. And then the sum variable is the sum of the first n minus k plus 1 elements in v. So the smallest n minus k plus 1 elements. And the final answer is just the sum of L plus sum of R minus what I am not taking, which is this sum variable plus 1. Okay. So this is the final code. Like the code is pretty obvious if you know the logic, but do you guys all get the logic? Is the logic clear? If it is not clear to anyone, please tell me in the next 10 seconds. I'll count down 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, let's go. Problem number C. You are the proud leader of a city in ancient Berlin. There are n square buildings arranged in a grid of n rows and n columns. The height of the building in row I and column j is h of ij. The city is beautiful if no two adjacent side buildings have the same height. In other words, it must satisfy the following. There does not exist a position such that h of ij equal to h of I comma j plus 1 and h of ij is equal to h of I plus 1 comma j. So all the adjacent pairs should not have the same height. There are n workers at company A and n at company B. Each worker can be hired at most once. It costs AI coins to hire worker I at the company A. After hiring, worker I will increase the heights of all the buildings in row I by 1. In other words, increase hi1, hi2 up to hin by 1. And it costs bj coins to hire worker J at company B. After hiring, worker J will increase the heights of all the buildings in column J by 1, or increase h1j, 2j up to nj by 1. Find the minimum number of coins needed to make the city beautiful, or report that it is impossible. Yeah, so problem C says that we have like n cross n city. So we have a city which looks like a grid of size n by n, right? And what we can do, like for each row and each column, we can increase it. Like let's say I increase this row, I increase this row, so we can increase the whole row by 1, or we can increase the entire column by 1. So we can choose any rows and columns and increase them by 1. Okay. And like let's say you increase this column by 1 also, and you increase this row by 1 and this column by 1, then this cell gets increased by 2, right? So that is one caveat of this. But this cell only increases by 1, and this cell doesn't increase by 1, so it doesn't increase by anything. Okay, so that's what you can do. But there is a cost associated with every row and every column. Like for the ith row, we have ai cost. So a1, a2, a3, a4. So for the ith row, we have ai cost of increasing the buildings, and for the jth column, we have vj cost. So let's say we have um, like if we want to increase this row, then we would have to pay a2 coins, and we can only increase this entire row by 1. Like if we have already increased this row, we cannot do it once more. Okay, so yeah, this is the problem, and we have to ensure that no two adjacent buildings have the same height after increasing. Like after we do the operations, no two adjacent buildings should have the same height. So what is the minimum number of coins to ensure that? Okay. So how do we do this? Now actually the first thing is that observe. There is one observation that okay, let's say we have 2 and 2 right here, right? Like let's say we have these two equal numbers initially in our input. We have these two equal numbers. Then what does that mean? It means that, like, of course, if I just do an operation on this row, like, if I do on this row operation, then it doesn't matter because it won't increase the or decrease the difference. Like it will make them 3 3. So to all such pairs, like to all the horizontal pairs, the operation on rows don't matter, right? Like whatever operation do I that I do on the rows, it doesn't matter to these horizontal pairs. And to the vertical pairs, let's say I have 3 and 3 right here. If I have 3 and 3 right here, it doesn't matter to them if I do a column operation. If I do a column operation, it doesn't matter to them because if I don't do, then also they will be same, and if I do, then also they will be same, but they will be 4 and 4, right? So this is one thing. Okay, now let's say, uh, so what I'll just do, like what I want to say is that what I can do, I can compute the row operations in one go. Like I will compute that what are the operations in the rows that I have to do. Like let's say for example, we have um, 1 2 we have, and we have 1 3, right? So basically we'll have to do either, like we have to increase this, right? Or let's take it 1 4. Okay, for now let's take it 1 4. So either we'll have to increase this or we'll have to increase this because of this vertical pair which is same. So that is row operation. But actually we don't have to do any column operations. We don't have to do any column operations because there are no horizontal pairs, right? So that's why we don't have to do anything. So basically we can just compute the row operations first, the minimum cost of row operations plus the minimum cost of the column operations. Okay, so actually how will I do this? So let's say we have this test case 1 2 2 2 2 1 2 1 1. Okay, so actually this is -1, so I won't tell this first. I will tell this one first. 1 2 1 2 3 2 1 2. Okay, 1 2 1 2 3 2 1 2, 1 2 1 1, and we have 1 3 1 2, right? So now just have a look at these first two rows. Okay, like just forget about these two rows, just have a look at these first two rows. Okay, so I have basically four possibilities, right? that I increase in this row, but I don't increase this row. This is one possibility, right? So let's write it as true. Like t t means that I have increased this row, and f means that I have not increased this row. Okay. So tf is one possibility. Then one is tt. tt is one possibility. Then one possibility is ff. One is ff, and the last possibility is ft. Right? These are four possibilities that can be done. Like f means that I do not increase this row, and t means that I increase this row. Right? But the thing is that not all of them are possible. Like, let's say I try to do tt. Okay, sorry. Let's say I try to do a tt. Then what will happen? Then these both will become 3 and 3, and 2 and 2, and 3 and 3. So that is the problem, right? Because we don't want adjacent cells to have the same number. So if we do tt, then it is not possible to do tt. Basically, it is not possible to do tt. So what I am saying is that if I have done a t here, okay, then I cannot do a t here. Also, the operation ff, it is also not possible. Like, if I it is not possible that I don't do an operation in both of these. So this one is also not possible because these two will remain same, like all of these three pairs. So ff is not also not possible, but ft is possible because it will increase this, and also tf is also possible, right, for these two rows. Correct? So that is one thing. But let's say for these two rows, I see for these two rows, tt is not possible because of this pair, ff is not possible again because of this pair, and ft is also not possible because of this pair. Like, if I do a ft on these two rows, then that means that if I increase this row, then this one will get changed to 2, and these two will collide. So that's why ft is also not possible. So the only possibility on these two rows will be my tf. This will be my tf. Okay. So that is one thing. Like, basically, it is fixed that I have to simply uh, increase this one and not increase this one. And since I am increasing this one, okay, since I'm increasing this one, I have to not increase this one. Like, because if I increase this one, then again I will get tt, and it is not possible. And for the final thing, since I am not increasing this row, I have to increase this row because I am getting this correlation of 1 1. So I'll have to increase this. So my final, this becomes constant, right? So actually, in this case, it became constant because we are very lucky. But in every case, it won't become constant. Like, there have to be multiple ways. There might be multiple ways of doing this, but we have to report the minimum cost of doing this, right? So yeah, that's what I'm saying, that according to the numbers, like, if you just choose any two rows, any two consecutive rows, let's say you choose these two consecutive rows, then out of the four options, tt, ff, ft, and tf, out of these four options, it is possible that not all of them are possible. Like, in this case, or let's just take the above one, let's just take the above two rows, the top two rows. Okay. So in this case, it is not possible to do ff and tt, right? It is not possible to do that. So what I'm saying is that what you do on the ith row, like, let's say this is your ith row. Okay, this is your ith row. So what you do on the ith row might depend on what you have done on the I minus 1th row, right? Because basically, if you have already done an f on the I minus 1th row, then you cannot do an f on the ith row. Similarly, if you have done a t on the I minus 1th row, then you cannot do a T on the ith row. So your decision on the ith row depends on what you have done on the I minus 1th row, and it doesn't matter the above ones like I minus 2, I minus 3. These rows don't matter because the adjacency only goes up till one row. So my decision of ith row only is confined to the I minus 1th row, whether or not I increased this row, right? So I can store that, right? I can make a DP. What I'll make is that, like, okay, let's say that what I'll do, I'll make a DP which will have like two states. Like one state is just I, that the first I rows. So let's say this I. So DP of I comma 1, or let's say DP1 of I, DP1 of I is equal to the minimum cost to handle first I rows. Okay, minimum cost to handle the first I rows if I don't do uh, an operation on the ith row. Okay, so what I am doing is that dp1 of I is the minimum cost to handle the first I rows. What does it mean by handle the first I rows? It means that to ensure that there are no collisions in the vertical form. So there are no vertical collisions. So to ensure that the minimum cost, to ensure that if I don't do an operation on the ith row, so that I am keeping track of that whether or not I have done an operation on the ith row or not. So dp1 is I don't do an operation on the ith row, and dp2, my dp2 of I will be that I have done an operation on the ith row. Now it is possible that it is not possible to do it, like, it is possible that it is not possible to fix these first I rows. Like for example, um, here if I say, okay, so these two rows if I see, um, so ft is not possible, ff is not possible, and tt is not possible. So in short, a t here is not possible. Okay, so basically my dp2 of this row, dp2 of I will be infinity, because it is not possible for me to sort, like arrange these first I rows if I do a true on it. Like if there's a t on this row, it is not possible. So my dp2 of I will be infinity, right? That is also one possibility. But essentially what I am doing is dp of I is the minimum cost to handle the first I rows if I don't do an operation on I, and dp2 of I if is I do an operation on I. And now, depending upon what is not allowed and what is allowed, I can easily make the transitions. Like I'll show you how to do it on this test case. All right. So it is just casework now, actually. Okay. It is just casework from now on. What I'll do is I'll make a DP table for you guys, or not a table. It is just two lists. Like it is just two vectors, DP1 and DP2. Okay. So what I am doing is, let's make a DP for this table. Okay, so dp1 is I change the ith row, and dp2 is I don't change the ith row. So let's write dp1 here and dp2 here. So if I change the ith row, or let's say I don't change this row, then what is my cost? It is 0, of course. Like till here I did not encounter any cost. And dp2 means I am increasing this one. So if I am increasing this one, then what is the cost? So the cost is just a of this, right? A of 0. So which is 1. So my, okay, now let's say we want this dp1. So dp1 means that I don't do here. So like I want a false here, I want a false here. So that means that because of these two, I have to have a false here. Like so dp1 of I plus 1, like dp1 of this row has to come from dp1 of this row. Oh sorry, my bad. Due to this pair, if we have a false here, then we cannot have a false here, right? We have to have a true here. What I'm saying is, due to this 2 and 2, we have to have a true here if we want a false here. So this dp1 of this row will come from dp2 of the above row. So uh, essentially it will become 1 plus what? Okay, 1 plus 0, right? Because on this one we are not doing, so it is just the value of 1. Like this dp1 of I plus 1 is just dp2 of I. And let's say we want true here, right? We want true here, so we have to have false here. So my dp2 of this row will come from only dp1 of this one. So it will be um, like 0 plus the cost of this thing, the cost of this row, which is 2. So 0 plus 2, which is 2, right? And that's how you can fill in the dp table. And if at some point, if you find out that all of the four possibilities are not possible, like if tt is not possible, if ff is not possible, if tf is not possible, and if ft is not possible, if all four are not possible, then just print -1, because you cannot do anything now. Akshat, the easy way, like what I am just doing is, see, on every row I have this matrix, I'll use that again. So let's say this is your input, right? This is your input matrix. Now on every row, I can either perform an operation or not perform an operation. So either true or false, right? But there are some constraints. Like because of this 2, I cannot have that this row is also a true and this is also a true. This cannot happen, right? And also it cannot happen that this row is a false and this row is a false. This also cannot happen. So you can only get the possibilities that either you can get tf, I mean t and f, or you can get a f and a t. So these are the only two possibilities that you can have. So what I'm saying is that what I do here, what operation I do here is dependent on what I have done at the last. So I'll just store that. Like I will just store a dp. That dp1 of I is the answer to sort the first I rows, or to make the first I rows correct. If I don't do an operation on I, let's say I is this one, I is 2, then my dp of I is the number of, is the minimum cost to arrange the first two rows such that I don't, so the second row is f basically, the last row is f, and dp2 is, my dp2 is that my last row is true. This is my dp, and easily you can transition by just checking that which transition not possible. Like here ff and tt were not possible, right? So you can easily just not transition them and transition from the other states. Like if you want to transition to dp2 of I, like of this row, dp2 you want, that means in this row you want true, that means in this row you have to have a false. dp2 of I will be dp1 of I minus 1 plus the cost of I, because you are doing an operation on I. So dp1 of I minus 1, that means you did not do an operation on I minus 1. So false and true, because dp2 of I. So this is a transition that you can do. And if you want dp1 of this row, that means you don't want to do an operation on this, so you want false here. That means you have to have a true here. So dp1 of I will be dp2 of I minus 1. So that's what you can just do. And in case there are both possibilities, like let's say that I have something, like let's say I have 2 3 and I have a 2 5, or okay, wait, I have a 3 5, right? So let's say this is my matrix. So in this case, my true false only, this is not possible because I have this 2 comma 3 right here. So TF is not possible. So FT is possible, TT is possible, and FF is possible. Okay. So what will I write? That my DP1 of I, that means the second one is F. So TF is not possible, right? These three are possible. So if my second one is F, like at the ith row it is F, then I have to have the first row as F, right? So my DP1 of I is equal to DP1 of I minus 1. And let's say I want DP2 of I. DP2 of I will be what? I want to have true here, right? If I have true here, I can have, see, if I have true here, then I can have either false or true in the first row. So I'll just take the minimum of them. Minimum of dp1 of I minus 1 and dp2 of I minus 1, and plus a of I will do because I am doing an operation on the ith row. So this is what you can do. Pradeep is asking, won't there be a case where FF will be valid if all the values in both those are different? Yes, FF can be valid also. Like there are 4 possibilities: TT, TF, FT, and FF. So they all can be valid in different cases. So let me just tell you that when they won't be valid. Like when will TF not be valid? When will TF not be valid? It will not be valid if in the adjacent two rows, if in the adjacent two rows, um, one element is something like this, that this one is X, and sorry, this is, let's say that this is X and this is X plus 1. Like the above element is X and the below is X plus 1. If there is an element like this, then TF is not possible. Then if an element is like this, that X plus 1 and X, okay, then FT is not possible. And if there's an X and X, like if there are two same elements, then TT and FF are not possible. So these 3 cases are there where you can just check that which ones are possible, and you can update the DP accordingly. Akshat, the DP is just like actually pretty standard. Like, have you done that problem where you are at, like the staircase problem, right? The staircase problem where um, you can simply either, so you are at the first staircase, 0 1 2 3 4 5. You are at the first staircase, you want to go to the last staircase, and you can skip at least one, at most one. So either you can go to 1 from 0, or you can go to 2 from 0. So if you have done that problem, it also just uses that 2 states of DP, 2 DPs. What is the first DP? Like DP1 of I stores that um, if I have, like, this is one way of doing it, right? This is one way of doing it. That DP1 of I means that I have not taken I. Like I have skipped I. I have skipped I. And DP2 of I means that I have taken I. Like I have walked on I. So in this one also, you cannot do FF. Essentially, that is the thing here. That in this problem, you cannot skip 2 stairs. So FF is not possible, but TT is possible, TF is possible, and FT is possible. So you can think of it like this, that this problem is also very similar to this matrix problem, but in this case, what is not allowed and what is allowed depends on what is in the matrix. Okay, but in the staircase problem, it is fixed that these 3 are allowed and this one is not allowed. Okay, so this is so that's what you will do for the rows. Like that's what you will do for the rows. So you'll get the answer for the row. So like no two vertical pair will be there, and the same thing you will do for the columns. Like you can just transpose the matrix and call the same function again. Like what I just did is I made a function and I transposed the matrix and called the same function again. So it will give me the answer for the columns, and then my actual answer will be the sum of those two. Like the total cost is the sum one, like the answer one plus answer two. Simply. Okay. So Akshay, did you get it now that how I have solved this? Like, do you get the transitions? What about columns? I just told you that whatever you are doing for rows, the same thing you will do for columns, right? Like, just write a function which will do it for your rows, and then just transpose the matrix and call that function again. So it will again do it for rows. But since you have transposed the matrix, now they are columns. So basically, what I'm just saying is that whatever you have done for rows, just do it for columns also, and your final answer would be just the row operations plus the column operations. Okay, Akshat, your final answer would be just that. Like for example, if I say we have 2 2 and 2 3, this is your test case, and your cost of the first row is 3, second row is 2, and the first column is 1, second column is 4. Okay, so what will you do? First you will try to figure out the rows. So since you have 2 2 here and you have 2 3 here, so what is not possible? FF is not possible, TT is not possible, and TF is not possible. So you are only left with what? FT. So FT means that your row cost is 2. So now, like, you have increased the rows. So you have got 3 and 4, and now you'll do it for column. For column, you want that these two should not be there, and this 3 and 4. So again, I think it is the same thing, that FF is not possible due to this, TT is not possible due to this, and TF is not possible due to this one. So only FT is possible. So you will do it for 4. So the answer is 2 plus 4, which is 6. And if you notice that if I just add 1 to the entire row, like, see, what you might argue that, 1 minute. If anyone of you knows how to fix this problem, then just tell me, just let me know. But yeah, so what I'm saying is that you might be asking that initially it was 2 2 and 2 3, right? But after we did an operation on this second row, it became 3 4, right? But if we compute the answer for the rows separately and the columns separately, then also it will give same answer, because the relative order of the element does not change. Like, see, in the rows, like let's say when I'm doing for the rows, I'm only concerned that is there any x and x plus 1 right here? Like, is there any x here and x plus 1 right here? Or is there any x plus 1 here and x here? Or is there any x here and x here? I'm only concerned about that. So even if I do so even if I have done columns before, like even if I have fixed columns before, so let's say I had done an operation here, like I just increased all of these by 1, then also this x and x plus 1 will be same. Like initially if it was 3 and 4, now it would be 3 and 4 and 5 if I have already done for the columns. So that remains the same. So it doesn't matter actually that which one you do first, row or column. You can choose, like you can do the operations independently and just add their answer. Pradeep, I think that's what you have asked, and I have already answered that just now. Like, yeah. So, do you get it, Pradeep? Pradeep, cool? Is it cool? Okay, cool. So yeah, this was the problem number C, and I'll show the code real quick. The code is very large because it is just casework. Okay, so I have this function which takes in the input of the vector and my cost array. Okay, this is my cost and this is my matrix, and it computes the cost for the row. Okay, for the rows it computes the costs. So I have n equal to v dot size, and I have these three booleans v1, v2, v3. So v1, v2, v3. What does that mean? V1 stores that if I have some operation like, okay, I have these three boolean vectors, right? I have these three boolean vectors of size n. Okay, so let's say this is the row I, this is the ith row, and this is the um, I minus 1th row. So my v1 of I equals to true. That will happen if I have some x right here and x plus 1 right here. So if this is the case, then I will set my v1 of I equals to true. Okay, or yeah, so if this is the thing, and if I have some x plus 1 and x here, then I will set v3 of I equal to true. And if I have x and x right here, then my v2 of I will set to true. Okay, so that's what I'm doing. For int I equal to 1, I less than I plus plus. Now I'm just iterating over all the elements of that current row. Currently I am at row I. So for the row I am iterating over all the elements of the row I. So if v of ij equal to v of I minus 1 j plus 1. So that means I have x and x plus 1. So TF is prohibited. So v1 of I is true and t1 is prohibited. TF is prohibited because if we do a t right here and f right here, then x plus 1 and x plus 1 will become same. Then if I have v of ij equal to v of I minus 1 j, then tt and ff are prohibited and I will set v2 of I as true. And if I have v of ij plus 1 equal to v of I minus 1 j, that means that I have x and x plus 1. If I mean x plus 1 and x, and I'll set v3 of I as true. Rohit, dp1 and dp2. So dp1 of I is my minimum cost. Minimum cost to make the first I rows, or the rows from 0 to I minus 1 or 0 to I correct. The minimum cost to make it correct if I don't do an operation at I. So if f at I means I don't do an operation at I, and dp2 is I, if it is t at I do an operation at I, that is dp2. Okay, so yeah, I was saying that I just make this boolean vector v1, v2, v3. Okay, now if for any row, if v1 of I is true and v2 of I is true and v3 of I is true, what does that mean? That if all three are true, that means that tf is prohibited, tt is prohibited, ff is prohibited, and ft is prohibited. So all four are prohibited. Prohibited means not allowed. Okay, for someone who doesn't know, prohibited means not allowed. So if all four, so basically if all three are false, then they are not allowed. So I'll return infinity. So infinity means that a very large value, so I'll print minus 1 in that case. And I have then dp1 and dp2. Okay, so the base cases are what? If I want to sort the first row, then it will not have any cost. Like if I don't want to do an operation on the first row, and if I want to do an operation on the first row, if I want to do an operation on the first row, then it will take me a0 cost, a0 cost. Then if I just iterate over the all the rows. So for int I equal to 1, I less than I plus plus. Now I have all of these cases. I have these 7 cases. Like, see, I have these 3 flags, right? v1, v2, v3. So either all can be false. So if all are, sorry, all can be true, right? So if all of them are true, then I'll just return infinity. But so there are total 8 cases, right? True, true, true. So I'll return minus 1, or I'll return infinity, which signifies that there are no solutions. Then we have true, true, false. Then we have true, false, true. So we have total 8 cases, and out of that, one I have already handled. So the other 7 cases, I have written an if else for that. Like, these are if else's. So if 1, 2, 3, 4, 5, 6, and 7. So I have handled 7 cases. Like, I'll just walk you through some of them. Like, let's say v1 I and v2 I. Like, v1 is true and v2 is true. Okay, so that means that tf is prohibited, and tt is prohibited, and ff is prohibited. So basically only ft is allowed. Okay, only ft is allowed. So of course we cannot make an f on this, and only ft is allowed. So dp2 of I, so t, and for I minus 1 we would have f, so dp1, so plus a of I. Then if we have v2 of I and v3 of I, that means that tf is only allowed. Like, ttff is prohibited and ft is prohibited, only tf is allowed. Because v1 of I is false, right? So tf is allowed. That means dp1 of I equals to dp2 of I minus 1, and I do not add plus ai because I don't do an operation on this one, and I do dp2 of I equals to infinity. And in the same way, whatever are allowed and not allowed, I am just doing transitions. So let's say, for example, if v1 of I is true and the other two are not true, that means that my tt is allowed, ff is allowed, and ft is allowed. So these three are allowed. Only tf is prohibited. Like, if my v1 is true, then only tf is prohibited. So if I want false at the second one, like, or at the current one, I'll have to have f at the first one also. So this is my transition. And for the second one, like, if I want to have true at the second one, then I can have either false or true. So I'll take the minimum of them and do plus ai. So this is what 7 cases I have handled. And finally I'll return the minimum of dp1 comma dp2. That is the minimum value of these two. Like, I can either do an operation on the final row, or I can not do an operation on the final row. So whatever gives the lower answer, I'll return that. Okay, so I'll just use this function to do it quickly. So int n c in n, and vector of wind v of n, and I just take c in v of ij, and I take the input of a and input of b, and I calculate the answer for rows. This is the answer for rows, right? Like, ll ans equals to an of v comma a. Then for int I equal to 1. So yeah, this is the row answer. And now I'll store the transpose of v in u. Like, I have another vector of vector, so I'll do u of ij equals to v of ji. So this just makes transpose. Okay, and now I'll do ans plus equals to the column answer. So answer of transpose comma b vector. So this is my total answer. Now if my total answer is greater than or equal to infinity, like, this is my infinity value, then see out -1, and otherwise I'll just see out the answer. This means that either the function 1 or function 2 return infinity, and that's why the answer is greater than infinity right now. And I have set this infinity to a very big value, this inf to a very big value. And yeah, so I just print the answer if it is not greater than or equal to infinity. So is it clear, everyone? Okay, clear. So I'll do a countdown till 10, or from 10 to 1 I'll count, and if someone has doubt, they can ask in that window. So okay, 10. Not that clear, Akshat? So uh, I think, like, if it is somewhat clear, then you should do it by yourself. Like, you should um, read the code. Like, okay, which part is not clear? Like, is there any specific part that is not clear? And like, if the entire thing is not that clear, then that means that you you should think of it by yourself. Like, if I try to explain it for more and more, then that won't be of any point. If you have still not gotten till now anything, like, if any part is not clear till right now, then that means you need to think it by yourself. Like, just think of it by yourself, and after doing that, just rewatch the recording, and I think you will be able to get what I was saying. And if you still don't get it, then you can comment on the YouTube video. Okay. So anyone else, like, do you have a doubt in a specific part? Then just tell me that. Why are you adding the columns? Answer means we want a combination of rows and columns, and not whole rows and columns. Uh, why am I adding columns? So see, that's what I actually told in the starting itself. Like, see, let's say I have some difficulties, right? Like, this is my matrix. Let's say I have 1 2 2, then 3 2 10, let's say, and I have 5 1 10. Okay, or let's just do 1 1 10. So what are the difficulties? Like, this 1 1 is a problem, 2 2 is a problem, this 10 10 is a problem, right? These three problems are there. So my point is that if you do the row operations, like, if you do row operations, then these two problems cannot be solved. This 2 2 and 1 1 cannot be solved, because it is obvious, right? If you just add 1 to the entire row, then again they will become the same thing, 3 3. And if you do an option on this one, then they still remain same. So that's why you cannot resolve this 2 2 and 1 1 using just the row operations. But, and also, you cannot resolve this 10 10 using column operation. Like, you will have to do a row operation on this 10 10, and a column operation on this 2 2 and 1 1, like, to fix these 2 2 and 1 1. So what I'm just doing is, first I'm trying to figure out the vertical objections. Like, I'm first of all ignoring these two, and I'm only handling this one. Like, I'm ensuring that there are no vertical dependencies or vertical same numbers while I'm doing the row operations. When I'm doing the row operations, I'm ensuring that there are no vertical dependencies. And so, okay, once I have ensured that, okay, then I can move to the columns. Like, I can do the column operations and ensure that there are no horizontal dependencies. And see, let's say I did an operation. I did an operation on this, like, to fix this 10 10. I do an operation on this one. Okay, so it becomes 4. Like, I'll write the new value with red. So it becomes 4, it becomes 3, and this becomes 11, right? So now this is not at all a problem now. But still, this and this is a problem. So I'll do it again with the row. Okay, I mean, I'll try to resolve this horizontal ones also using the column operation, right? And I can do that. So, like, separately I'll do that. So basically, to resolve these, what I can do, I can just increase this row. So if I increase this row, it will become what? This will become 3, this will become 4, and this will become 2. So now, as you can notice, that the new values and the old values, so the new matrix is not causing a problem. So what I have done is, I have operation on this row and on this column. So my total cost is what? The cost of the rows plus the cost of the columns. So I think I should be clear right now. Akshay is saying that we don't want whole rows and columns. Like, I don't understand what you mean by that. What do you mean by whole rows and columns? We want whole, right? We cannot do operation on partial cells. Like, one operation we can do only on the entire row. On the entire row we can do operation. Okay. All right. So I'll move on to the next problem, D. And actually, this is a nice problem. Like, um, one second. Yes. Anyways, so this is a nice problem, and why I say that is, like, I'll tell you. Okay. If my Chrome works. Anyways, so you are the proud owner of an infinitely large grid of light bulbs represented by a Cartesian coordinate system. Initially, all of the light bulbs are turned off, except for one light bulb where you buried your proudest treasure. In order to hide your treasure's position, you perform the following operation an arbitrary number of times. Choose two integer numbers x and y and switch the state of the four light bulbs at xy, x y plus 1, x plus 1 y minus 1, and x plus 1 y. In other words, for each light bulb, turn it on if it was off and turn it off if it was on. Note that there are no constraints on x and y. So there are no constraints on x and y. In the end, there are n light bulbs turned on at coordinates x1, y1, x2, y2, and xn, yn. Unfortunately, you have already forgotten where you have buried your treasure. So now you have to figure out one possible position for the treasure. Good luck. So yeah. And okay, in the input, basically you have the points. You have the points which are on right now. And also it is guaranteed that there exists at least one position such that if the light bulb is initially turned on, then after forming, so basically the answer always exists. The answer always exists. That's guaranteed. Like, they have already guaranteed us that the answer exists. And also one more thing, hacks are disabled. For this problem, hacks are disabled. Like, this is also one more hint actually that I took to solve this problem. Okay. So let us actually think about this. The problem says that you have a grid of infinite light bulbs. Okay. So let us draw this grid by this square grid, rows and columns. Okay. So initially, only one light bulb is on. This X means on and empty means off. Okay. So initially only one is on, and in one operation, what you can do is you can choose X and Y and switch the state at xy, xy plus 1, x plus 1 y, and x plus 1, sorry, x plus 1 y minus 1, x plus 1 y. So basically you can just choose any vertex. Let's say you choose this one. So this is x comma y, and let's say my x axis and y axis I'll draw. Okay, so this is my x axis and this is my y axis. All right. So um, let's say you choose this xy, then you can switch the position xy, xy plus 1, xy plus 1, x plus 1 y minus 1, x plus 1 y minus 1, and x plus 1 y. So these four you can simply switch. Like, if they are on, then you can turn them off, and if they are off, then you can turn them on. And basically, initially only one bulb is on. Okay, and you can do operation of these type. And finally, what you can do is, well, like, what you have to report is that, okay, you have been given, like, in the input you have been given some light bulbs which are on. Like, all of these light bulbs are on. Okay, so you have to tell them that what could be the initially on position. Like, initially there is only one on, right? Initially only one light bulb is on, and in each toggle you can toggle these four, like this kind of shape you can select. This kind of shape you can select on the Cartesian plane, and you can toggle them, and simply you have to tell them that what could be the initial position of that light bulb which was on, given the final state of the light bulbs after doing the operations. Okay, so is the problem clear? Like, I think it should be clear that initially there is a light bulb which is on, and in one operation you can toggle the light bulbs in this shape. Like, at any position you can choose this shape, right? And you can toggle the light bulbs. That means if it is on, you turn it off, and if it is off, then you turn it on. Okay, and yeah, you will just do this. So how do you solve this? Now, actually, after reading the problem, it seems quite tough, right? Because this shape is pretty complicated to understand. Like, many things are happening. So actually, the thing is that um, yeah. So this is my x-axis. This is my y-axis, and the shape that you can choose is this one, right? Rajat didn't get the problem. Okay, so I'll tell the problem again. So okay, Rajat, let's assume that this is your Cartesian plane. Okay, so this is your Cartesian plane, and this is the point 4 comma 3, right? This is sorry, 4, or maybe 0 comma, this is 3 comma 2. So this is 0 1 2. This is 0 1 2 3. So this cell is 3 comma 2, right? And what you can do is you can select any one shape, like you can select any one position, or basically you can select any one xy. So let's say you select this, then you will toggle this one, then also you will toggle this one, and this one. So after you perform this operation, then what will happen that uh, initially the 3 2 was on, right? So now it will be off, and these three were off already, so now they will be on. Okay, so this one is off, and like all of the others are off, like all of them are off. I'm not drawing them, but they are off, and these three will remain on. Then let's say again you do an operation like this, like you do this, like let's say you operation on this thing, uh, let's say you do it on this thing. Okay, these four cells. Then what will happen that um, these two will become off, like these two will become off, and these two will become on. Okay, so let's say that finally in the input you have been given that the cells 3 comma 3, um, 5 comma 0, and 5 comma 1. So these three cells are on. So let's say you have been given that these three light bulbs are on. So you have to tell them, you have to output that what is one possible position of the initial light bulb. So as you know that the initial light bulb, this was on, right? The 3 comma 2 was on, and from that, like from that position, we got till here, where these three were on. So we have been given that these three are on, and we have to report any one possible position which is possible such that these light bulbs are on, and it is guaranteed that the answer exists. So in this case you can output 3 comma 2. Like if you have been given these three light bulbs, like you have been given n equal to 3, And given that these three are on, then you can say that initially 3 comma 2 could have been on. So Rajat, do you get it now, that what does the problem mean? That you have been given these n bulbs, and you have to report that which light bulb could have been the origin of that. So yeah, this is the problem. And actually, to solve this, it is actually very, like, non-conventional, I would say. So see, the first thing that I took is that the answer exists. Like, they have guaranteed that the answer exists. Okay, like, we don't have to tell them whether it is possible or not. They are telling us that whatever the input they give us, the answer always exists. Okay, and the second hint is that hacks are disabled. And so why could hacks be disabled? Let's think about that. Like, I thought in this way, that why could hacks be disabled? That would be because they don't actually have a solution. Like, it is possible, like what I guessed is that even the authors don't have a solution to the problem. Like, even they cannot tell, like, given an, let's say I give them an input, then even they cannot tell whether a solution exists or not. Like, even they cannot tell whether solution exists or not. So that's why hacks are disabled. Because if hacking was on, then I could give any input. Like, I could give that input also, on which the answer doesn't exist, and they will, and apparently they are not able to tell that answer exists or not. So basically, their solution also relies on the fact that the answer exists. Like, they don't have a solution which can predict that um, the answer is there or not. Hacks are disabled means that, do you know hacking? Like, hacking means that basically you can um, like, see other codes. Like, basically in div 2 you have a room. So in your room you can see other people's codes. If you have already solved it, like if you have already solved a problem, if you log a problem, you can see other people's codes and try to give an input. You can try to give an input for which their code fails. That's called hacking. Okay, so since that is disabled, then that means that they don't have actually a validator. Like, okay, just forget. If you don't understand what I said just now, just forget what I said. Like, that is not relevant. It is just how I thought. Okay, so yeah, hacks are. So anyways, what my solution is, just observe it. Just observe one thing. Okay, just observe one thing. Okay, like, what is the pattern that we are allowed to do? Like, in one move we are allowed to do this, right? We are allowed to toggle this entire box. Like, we cannot toggle one single bulb. We can toggle only this entire box in one move, right? So you can just observe a pattern. Like, what pattern can you observe? So one thing is that for any x value, like, for any x value, just think about what I am saying. I'll write it also. For any x, I can only toggle even number of light bulbs. Right, guys? Like, do you get this? For any x, I can only toggle an even number of light bulbs. See, why? Because the operation that I can do it like this only. So if I am doing an operation on this cell, then I am doing on this cell also. So in this row I am doing two toggles, and this row I am doing two toggles. So in every, for every x, I can only toggle even number of light bulbs, right? So do you guys get this point? So I can actually use this to my advantage. I can use my advantage. And how do I use that? So let's see. So let's say I give you a grid, and I tell you, okay, that uh, this is row 1, sorry, row 0, row 1, row 2, row 3, row 4, row 5. Okay. So let's say that this light bulb is on, this 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 is on, and this is on, and this is on, and this is on, and the others, all others are off, like up till infinity, and up till minus infinity, all of the others are off. All the other light bulbs are off. Okay, and only these ones are on. So guys, actually, can I say that my light bulb, the initial turned on light bulb, lies in the second row, like x equal to 2, x equals to 2. I can say that. Like I can always say this, that my the initial light bulb lies in x equals to 2. And why can I say that? Because, okay, what I claimed was that for any x, I can only toggle an even number of light bulbs. So what does that mean? That initially, let's say for some row, like let's say this is some x, I'm isolating this x, let's say this is x equals 2. So for some x, this entire column of the same x has, let's say, odd, let's say it has odd number of on light bulbs. If it has odd number of on light bulbs, then if I do an operation on this, like my point is that always it will remain odd. Then always it will remain odd. My point is that if there are odd number in a row, like for let's say x equals to 2, there are odd number of points at which bulb is on. Then whatever operation I do, always it will remain odd. And like let's say I had come from a state to this state, then in that previous state also there must have been odd number of bulbs on. Okay. So initially initially we knew that only one bulb is on, right? In the entire grid, only one bulb was on. So let's say here. So my point is that whatever operations you do in all the rows except this row. So let's say x equals to 2 you have. So all of the x's except for 2 in all of these rows, this row, this row, this, or column, whatever, like you can call it row or column or whatever. So for all of these columns, you will always have even number of on light bulbs, and for this column you will always have an odd number of on light bulbs, because initially it is odd. And if you can only add or subtract 2, like if you can only toggle 2, like if you can only toggle an even number of light bulbs for any row, then odd will remain odd and even will remain even. So that means that that row in which there's an odd number of x, that is my row of the answer. Do you get this, guys? Just tell me, is it clear till now? That since for any x, odd will remain odd and even will remain even. So initially it was odd where my answer lied. So finally the odd row, that has to be my answer. So now I have gotten the x value. I have gotten the x value for my answer. But now what about the y value? So to find the y value, actually you can notice one more thing. What I noticed is that, first of all, in each x these two are there. But second thing I noticed, that even this is also one more thing. Like if you also isolate this as these two, like just think of it like this, that for any x plus y, see this line is what, on this, like on all of these cells, on all of these cells, the value of x plus y is fixed, right? The value of x plus y is what? 4. For all of these cells, the value of x plus y is 4. And for all of these cells, the value of x plus y is 5. So, what I can say is that for all of these cells, like for a certain x plus y, like see, for a certain x also, I said this, that always for any x, I can only toggle even number of light bulbs. I can say the same thing for any x plus y also. Like for any x plus y value, if I am toggling this one, then I am toggling this one also. So I can only toggle an even number of light bulbs. For any x plus y value, I can only toggle even number of values, even number of light bulbs. So the same thing I can apply, that for any x I can only toggle even number of light bulbs, and for any x plus y also I can only toggle even number of light bulbs. So I can use these two facts to my advantage. So guys, do you get this part, x plus y part? Like how for any x plus y only even number will be there? Can you get that part? Okay, so since even for all x plus y, I can only toggle even number of times. So see, what I can do is that, like, let's just take a test case now. 726, 627, these are very big values. Why do, okay, let's take these values: minus 2 minus 1, minus 1 minus 2, minus 1 minus 3. Okay, so we have 1 point here. This is minus 1, this is minus 2, this is minus 1, this is minus 2. So we have minus 2 minus 1, which is this one. Then we have minus 1 minus 2, uh, this one, and minus 1 minus 3. So this one, right? So as you can see, for this x plus y, like for this x plus y, which is x plus y equals to minus 3, we have an even number. We have an even number of cells which are on. But for this x plus y, which is x plus y equals to this is minus 8, so for x plus y equals to minus 4, I have only one. I have only one. And also for x equals to minus 1, like for x equals to minus 1, I have an even number, like I have 2. But for x equals to minus 2, I have only odd number. So this is even, and these two are odd. So since they are odd, then what does that mean? That initially also they have to be odd. And what does that mean? Like initially there's only one cell empty, there's only one cell on, right? And if initially x plus y is odd, that means that my answer lies in x plus y equals to minus 4. And if initially minus 2 is odd, x equals to minus 2 is odd, then that means that my initial answers x coordinate is minus 2. So I know that my initial coordinates x coordinate is minus 2, and my x plus y is minus 4. So I can say that my answer is minus 2 comma minus 2. And that's how you can do that. Actually this is because you know that the answer exists. It is guaranteed. Like it might happen that even though there is only one odd value, like out of all the ones, there's only one x plus y value for which there is odd, and one x value for which there is odd, but there doesn't exist any point where you start and you end up at this state. So it might exist, it might happen that the answer does not exist, but it is guaranteed that for all the inputs that you are given, the answer will exist. So you can leverage that fact and just say that if my answer exists, then it has to be minus 2 comma minus 2. But how can someone come up with a solution in the contest? So that's what I told you, right? Like we just have to look at some invariants. Like I thought of it like that even these guys don't have a solution. Like the fact that hashs are disabled, that means even these guys cannot comment that for a given input, does there exist does there exist any um, answer or not. So that means that the intended solution has to be something like which uses the fact that the answer exists. That means I can, if I can find some invariants, like invariants for this, what does that invariant mean? Invariant means that over, if I perform the operations, like if I perform all the operations, then my answer, like something that doesn't change. Like if I perform some operations, then for any x, the parity of that the number of light bulbs does not change. So that is an invariant. So I was thinking that there has to be an invariant which does not change, and I can exploit that to get to my final answer. So and the invariant in that this case is this thing. Invariant is this thing that for any x there has to be, the parity should be the same if I perform the operations, and for any x plus y the parity of the number of light bulbs has to be same. And like I actually observed this by drawing this figure. Like I just drew this figure, that here and here. So what is constant? This x plus y, this line x plus y, right? Like this line is x plus y equals to constant. Like if you know a bit of coordinate geometry, so if you draw this line, this is x plus y equals to constant, and this line is x equals to constant. So for both of these, my number of bulbs parity does not change, and that's how I uh, saw the solution. So yeah, what I'm saying is just look at all the x's and look at all the x plus y's, and for whichever value there is an odd number of light bulbs, that will be your answer. Like that will be your answers x and your answers x plus y. And you can, if you have an x and you have the x plus y, then of course you have the y also. Y is just your x plus y minus x. Yes, so that is your answer. And yeah, this problem is very nice. Like I mean, for someone who didn't solve it, maybe they will curse at this problem, but it was pretty elegant, to be honest. But yeah, there is a solution right here. Akshat, if your approaches are different, but your answer is accepted, like if your code is getting accepted, then no problem. Like it doesn't matter, because if it is, yeah, the entire motive is to get accepted. But yeah, if possible, you should look at the tutorial also. Like after the contest, if you think that your solution might be different from the editorial, you can look at the editorial and just see that what they have used to expand your knowledge, like so that you can use that method in the future. But if you have solved using some other method and it is accepted, then it is no problem. Okay. Anyways, so I'll show the code for this one. The code is pretty small. It is accepted now. uh, my bad, I'll show the code here. Okay, this is not the code. uh, okay, I'll have to do something. Let's do a VPN. Wait. Okay, is the screen visible? Am I audible? I think I should be audible. Yeah, so this is the code. Int n, c in n. I made two maps to count the frequency of x and x plus y. So int xy, c in xy, m1 of x plus y plus plus. So I am counting the number of points which are at some x plus y, and m2 of x plus plus. Okay. So for certain x, how many values are there? Then I have, so these m1 and m2 maps are there. Now I'll just search for that key for which the value is odd. So I'll iterate over all the key value pairs, and if x dot second, which is the value, if it is odd, then that is my value of x plus y. So my x dot first is my key, right? So v1 is x dot first, and I'll break. So basically the current value of x plus y, that is my answer. And for the same thing for x, I'll do my v2 is x dot first. So basically I am storing my x plus y in v1 and x in v2. So yeah, see out v2 and v1 minus v2. So since my v1 was x plus y and v2 was x, so I'll see out v2 and v1 minus v2 and new line. So yeah, I hope it is clear. Naman says XOR of all x values and XOR of x plus y. Okay, yeah, that is a nice approach. Nice. That is a pretty nice approach. I mean, I can just implement this in 1 minute, I think. That is okay. I'm impressed, actually, to be honest. So, yeah, to show you how fast that is, I'll implement this on your screen. So, LL xy, in xy, uh, v1 XOR equals x, and v2 XOR equals x plus y. See out v1 and v2 minus v1. So I think that should work. I mean, yeah, that is pretty smart because you want that value um, which comes odd number of times. So yeah, it should be working fine. Yeah, it is giving the correct answer. Nice. So I'll submit this also. I'll share this code as well. Anyways, so this was the solution, and I hope it is clear to all. Like, if anyone has a doubt in this, any problem from A, B, C, D, they can ask right now. Or maybe if you have a doubt in D first, I'll take that. But if it is clear, then I'll take your leave. Okay, so guys, do you have any doubt? Just tell me if you do have any doubt. I'll give you 30 seconds to ask. So, or let's say, Akshat, I don't think I'm allowed to do that on this live stream. Any other doubts? You can DM me on Codeforces. All clear. Thank you. Okay. Thank you, Rajat. Okay. Devil Boy. I can't comment on that. You can mail TLE Eliminators. So there's a contact us section at the website. So you can just mail there. Problem E, actually, I wasn't able to solve. Like, I tried, but um, I did not solve it. If you can see, like, I was getting wrong answer. Like, I actually boiled down the problem quite a lot, but I still couldn't solve the boiled down problem. If so, I can't comment on that. And Devil Boy, you can go to this contact us section. Where is it? Yeah, contact us, and they will get back to you. How to DM on Codeforces? You can go to your account and uh, write new entry. Wait, not new entry. Wait, not this. View my talks. Okay, not that. Okay, let's say I want to DM tourist. Then you can go to his profile and talks. Okay, and you can write send message, and you can write here whatever you want to write. I won't send this, but yeah, that's what you can do. All right. So I think everything should be clear now, and I'll take your guys' leave. So bye bye. Thanks for joining in, and I'll see you guys later.